Okay, today we are going to chapter 4 and problem 7 and problem 8. So for problem 7, a localized distribution of charge has a charge density like below. In part A, make a multiple expansion of the potential due to this charge density and determine all the non-vanishing multiple moments. Write down the potential at large distance as a finite expansion in Legendre polynomials. So first, we know that the Legendre polynomials for L equals to 0 and equals to 2 has a formula like this. And we change our sine square theta here into 1 subtract cosine theta square, and then that equals to polynomial. We expand in polynomial, Legendre polynomials, and we have the result here. The sine square theta equals to this one. And next, we change the sine square theta in the charge density here, and we change it into this one. And next, we do the integral to calculate the multiple moments here. We calculate our multiple moment here, and we have the integration like this. And next, we will do the integration. And because of the orthogonality, we only n equals to 0 and the L equals to 0 and 2 terms will survive. So, so we can drop into these 2 terms, L equals to 0 or equals to 2 with the relation here. So we cancel the cosine theta's integration. And next, we cancel the phi integration here into 2 pi. And next, this one will change into the gamma function here. And because of our L has only equals to 0 or 2, so we have the result here. We have Q00 and the Q20 here on left. Okay, so we only have these 2 multiple moments. So next, we will calculate our potential. As a potential at a large distance here, we can write down in this formula because of our multiple moments. So we use these 2 multiple moments, and our spherical harmonics will change into, because of our spherical harmonic will change into y00 and y20 here. So and next, we apply the result and just sorting our coefficient. And finally, we'll get the answer here. This is our potential in Legendre polynomials. So this is for part A. For part B, determine the potential explicitly at any point in space and show that nearly a region correct to R squared inclusive. Our potential has the form like this. And since there is no conducting surface, the green function here is simply just have a relation here, has a form here, and we just imply the green second theorem, and we take our boundary surface infinity. So here only the volume integral left. So we do the volume integral here directly and likely with the orthogonality. Only these 2 terms survives. Okay, so this is our potential, and next we will deal with the R smaller and the R larger next. So to deal with the R smaller and R larger, we have divide our integration into two parts for 0 to r or r go to infinity. So we have these two integration, and we apply our limit. We apply our L. Our L only has two values. So with L equals to 0, this integration will have the result like this with our integration by parts. And for L equals to 2, the integration will give our result here. Okay, so here we have two series here for r equals to 0 or r equals to 2. For L equals to 0 or L equals to 2. We have these two series. And finally, we can calculate our potential. And with a Taylor expansion, we expand our exponential minus r into these two series. And okay, well, we apply the Taylor expansion. We change our exponential minus r into this series, and only okay. So we correct to r squared. So finally, the answer will like this. Okay, so this is for part B. For part C, we need to we change our charge into we look into the nucleus with a quadrupole moment like this, and so we should change our, because we first know that if we put the correct unit of electronic charge E and ball radius A0 into the charge distribution rho, the potential near the origin becomes just like this. Or we look into the nucleus, so we change our potential, we modified our potential going to this form to and next we calculate the work here. So we just do the integral over the space between the charge of the nucleus and the potential inside. Okay, so we just do the integral. So here our low volume integral will give us a z. Z is the number of the charge number, total charge number of the nucleus. Okay, so so we do the integration and go next. We change our cosine squares. We change this into this one. So because of our direction. And next, for Jackson equation 4.9, we can change this integration into our multiple moments here, or our quadruple moment. So and next, we drop in the first term, the monopole term. We only left this one because the part C only acts the quadruple moment interaction here. And next, we sorting our coefficient into fine structure alpha here. And we have an approaching, and this is about 1 megahertz here. So where we have the fine structure constant, we'll have the value like this. So this is for our part C. So go next, we will go to problem 8. Problem 8, a very long right circular cylindrical shell of dielectric constant here, and the inner and outer radii A and B respectively is placed in a previously uniform electron field here, with its axis perpendicular to the field. The median inside and outside the cylinder has a dielectric constant of unit. Part A, determine the potential and electric field in the three regions, neglecting end effects. So first, we just do a general expansion for our cylindrical coordinates. So we have, and then we matching our boundary. We have some coefficient will go to 0 here. And next, we keep matching our boundaries here. So for now, we have a small summation here, a small common here, like for our potential. And next we find the electric field on rho direction and phi direction here. And next we continue. We keep matching our boundary for check the continuity at r equals to rho, at rho equals to a and rho equals to b. We have another coefficient direction here. So next, we just do the heavy calculate. So for our convenient, we take this one equals to triangle. So we can sorting our coefficient like this form and go next. So finally we can finally we can give our potential like this. After we finish the heavy calculation, and our electric field will have the form like this. So this is our answer for part A. And for part B, we schedule the lines. For the case B equals to 2 times A. So we have a line like here, like this, okay? And for part C, discuss the limit forms of your solution appropriate for a solid dielectric cylinder in a uniform field and a cylindrical cavity in a uniform dielectric. Okay, so for a solid dielectric cylinder in a uniform field, we just let our inner radius approach 0, right? So we have a result like this. And for a cavity, we just make our B approach infinity. We will have our cavity. Okay, so you have the result here. So this is for our part C. So today our 2 problems are finished. So see you next time.